Part 2 of my presentation. This time I would like to underline the previous technical discussion with some case studies. So yeah, let's start with that. I have 3 case studies here for you. So the first one is with AstraZeneca. The second one, I may not name the tablet, I may not name the customer, so we just call it active ingredient A tablets. And on the third, we have our case study with Novartis. So let's directly go to the first case. So our AstraZeneca. So here you can see the used tablets. So at the end we have 3 tablets with a 6mm tablets. With these tablets we just make some mass measurements, no NIR at all. And then we have an 8mm tablet with a high dosage. So it's 50 milligram API. The nominal mass is 164. That means we have a nominal API fraction of 30.52%. On the other hand, we have a low dose product. So this is the 10mm tablet. So we see here the API label claim is here 8 milligram, nominal mass 400. That means it ends up here with only 2%. And this will maybe also answer your question regarding low dose products. Let's go to the first results. So what we applied here is a test, a long-term run with a maximum speed in the CU120 with 120,000 tablets an hour. Here you see the tablet prediction of the 6mm tablets in terms of the tablet thickness. So you can see here, this is the reference with the 4-parameter tester, and this is the result from the laser scanner. So you see a slight difference, but you see that the standard deviation of the measuring itself is 0.02 for the 4-parameter tester. This is the physical reference station where you have the kind of application measurement tool what is measuring on a physical basement. And here is our laser scanner with an overall standard deviation of 0.08 millimeter. On the other hand, so we have here our mass prediction. So this is also measured by the 3D microwave in full speed, 120,000 per hour. And here we just took out 20 samples. We measured them with, you know, in the bottom is the external scale. So we just measured them with them. We compared these values to the supplied values from the CU. And here you see then just the appliement. So you see it is really following. And you see that the standard deviation of these measurements is around 0.2 milligram. So before, you remember, I told you the overall accuracy is around 1 milligram in the 3 sigma process. So here, just below that. Going to the NIR measurements, so here you see the experimental setup. So we start first with the CU120. Here we applied with our NIR a triple measurement on 7 tablets. So we have 7 kind of calibration tablets. So only we were able to use 8 reflection fibers. So I told you before that we have 9. Unfortunately, 1 was broken. So 8 collimation fibers. Here you see the distance from the probe, you see the integration time, you see the conveyor speed. Not that important for our study now. But here the number of spectra collected per tablet is 16. It means we were able to apply 2 images on this tablet. So this is what the laser scanner calculated with the dimension of the tablet, with the band speed. 2 images per tablet. Usually it should be 18, but as a result that 1 fiber was broken, the overall number of spectra here is 16. Good. Comparison in this case. So AstraZeneca used an NIR reflection spectroscopy with a lab spectrometer. So I think it was some Bruker tandem, something like that. Also here, these 7 tablets were measured on both sides with a single measurement. And the second method here, reference method, was transmission Raman spectroscopy Also here, the 7 tablets were measured from one measurement from each side. Regarding our CU120, so we know we have to do some chemometrics. The best visualization of the outcome of the chemometrics are different plots. I know everybody is using a little bit some other plots for doing like that. I like this representation. So what you can see here is the Hotelling squares. So this is really telling you if your samples, what you build in the model, are very equal with them what you measure. So for example, if you would have a foreign API, so a completely different drug, so you would see this immediately in the Hotelling t-square statistics. Then you have the leverage versus residual plot. The most important is, of course, actual versus measured. Here you see the results from the transmission Raman or from the NIR supplied by the reference analysis, and of course what we measured with our CU120. And the scores you see here that you have completely distributed samples. The results. So they are summarized in this table here. Let's first take a look on the 8mm tablet. This was with high dose, the 30.52% drug load. So we see here CU120, the lab spectrometer and transmission Raman. We see the wavelength range, what were used for calibration. We see the pre-treatment, so the mathematical pre-treatment to bring the spectra in a form that they have the most correlation with the property, so with the API fraction. We have the bias, and we have here, what is probably most important for you, the root mean square error of prediction. So this is the deviation, the accuracy of the system. So, and here is also the used numbers of factors. So let's have a look on the RMSEP. So the CU120 ends up with 1.56, lab spectrometer 1.63, and the transmission Raman also very equal to 1.62. So at the end, they were all performing in the same range. But here, please, I would like to remind you, these two methods here are lab spectrometer. That means these methods take 1 to 1.5 minutes per measurement for one tablet. This method here, our CU120, we talk about 120,000 tablets per hour. So, and you see, they have the same performance as a lab spectrometer in the case where we have a high drug load in the tablet. Second example, we have here our 10mm tablet. This was the low dose drug with 2%. And here we see differences. We have also here the wavelength range, we have the pre-treatment, we have the bias. And here we see now CU120 is around 3.8. Lab spectrometer, the NIR, even worse with 5.44. And best works here, Raman transmission with 1.97. But again, they have time. They really needs or takes 1.5 minutes per measurement per tablet. So let's take a look on the conclusion for the first case study. So we did successful high-speed spectra acquisition on the 6mm tablet. High-speed run with 6mm tablet. This was not for NIR, this was just for the mass and the thickness verification. So the thickness and the mass were predicted with the following standard deviations at a speed of 120,000. Thickness was 0.08 and the mass was 0.02 milligram, the comparison between the 4-parameter tester and the 3D microwave. For the 8 and 10mm tablets, we have seen that Raman gave the best results for the low dose 10mm product, but all three techniques showed the same, let me say, performance for the high dosed 8mm tablets. Let's go to case study number 2. So this is the tablet. What name I may not tell you. We have here a label claim of 125 milligram. That means we have a nominal mass of 850 milligram, and we can calculate a nominal API fraction of 14.71. So it's between the slow one, and the high dosed application tablet. So also here, let's start with the measurement on the CU120 with the mass. So here we just took 10 samples. That means these are the samples from the reference, from the 4-parameter tester. These are the predictions by the CU120 3D microwave. You see the difference, and we just applied the difference, and you can also see that the standard deviation here is 0.38, still in our, let me say, what we claim to do below this 1 milligram accuracy frame. For NIR, so we took also tablets with different API content. So here we have not really much access on HPLC data. So the reference analysis, the data were provided by a lab spectrometer. Okay, so we have to take these results from the lab spectrometer, and with these results we have to calibrate our NIR. It means we might have the mistake or the prediction error of the reference method plus ours. Just that you have this in mind. So here you see the different NIR spectra, what we collected from spectra with varying API contents. You see here, this is not that good, so we have to apply any pre-treatment to visualize a little bit where are my point of interest in the spectra. So we did here, we applied the mean centering and then standard normal variate. These are typical mathematical pre-treatments. And with that, we can see where are the regions of interest. Here we have variation. Here we see the different API content. Okay? So also that we brought then to a model. So we see here the scores. Here we can easily very nice see that we have in the scores a different direction of the API content. Yeah? And we see also here the measured versus predicted. And we see here the model data. You have the root mean square of calibration, of cross-validation. You have the root mean square of prediction, and so on. And here in the table, I just summarized the most important for you. So wavelength range, the pre-treatment, and here the most important, the RMSEP, the root mean square of prediction, was 2.07%. Please keep in mind, this is including the prediction error of the lab spectrometer, where we get the supply of the reference data. Now I would do something what is maybe dangerous, but I would like to show you also, if you make high-speed runs, I would like to compare that. And unfortunately, I told you I don't have reference data available, reference data based on HPLC. So what I can do, just to compare that we are really on the right track with our measurements, is I can do a data population comparison. And this is what I did. So I just have a speed with 120,000 tablets. In the population 1, I took 30 tablets. They were measured by the NIR lab spectrometer and the weighting cell, so out of our machine. And the second data population, these 40 tablets, were measured by our CU120 with the speed of 120,000 tablets an hour. Good. Then we have here the results. That means we have now to compare the API fraction of population 1 with API fraction of population 2. And of course, the content uniformity, if we also take the mass of these tablets into consideration of population 2 with the CU. So you see that they are in the same direction. That means the CU120 works for really content uniformity inspection. Let's also summarize these results here. So we applied successful high-speed data acquisition and a comparison of the 3D microwave and the external scale, the weighting cell data, with a standard deviation of 0.38 milligram. So we are still in the required thresholds. So we performed successful high-speed spectra acquisition again on these tablets. The NAR model results in an RMSEP of 2.07%. That means the prediction of the CU120 are within the required root mean square error of prediction. And we can say that the CU of each individual tablet can be predicted in high speed. And because I was facing these questions from some of you guys already, this customer is using the machine, or is going to using the machine for a real-time release. This is the way how he wants to use the machine. Okay, last study. So here I have a case study with Novartis. So also here we have the tablet. So the label claim is 87.5 milligram, nominal mass 350. It means we have a nominal API fraction of 25%. So anybody from you knows this nice formulation? Who is good in chemistry? It's diclofenac. Okay, same way. First we have to do spectra acquisition. So here you see the raw data from spectra with varying API content. Also here we have to look what is the best wavelength range, what is the best data pre-treatment to visualize where we have variation in the spectra. So we found out that we have between 1060 to 1240 nanometers. We see here with an SNV again, I think this is the most liked data pre-treatment of our engineer. So we see that we have here the variation of diclofenac. This results now in our model. So we have here the measured diclofenac versus predicted. We have also the scores plot. Also here we can see we have a direction from the low dose up to the high dose product. Low dosed, high dosed, these are my calibration samples. So we took samples from 75% drug load up to 125. And this is what you just see here. 175, 80, 85, and so on up to. And this is very important. If you see in the scores that you have a main direction, you know that your NIR model is sensitive for API fraction. This is very important to know. Let's also see some results here. So the first what we did, we just took one tablet and passed it many times through, I think 100 times. We passed it through the CU120, and then we look for the mass and for the API measurement. So we just look for the reproducibility of one tablet. So the mass measurement, you see here, these are the results. And here, this is really a screenshot from the HMI, what you can get out. And you see here deviation, the throughput, the measured weight, and there's also the average, where's the min max, and there's also this, there. And here's the standard deviation, it's below 1%, so 0.89. Okay? Oh, sorry, before I just go to the next slide, of course we did the same here for the API measurement, and oh, this is small. Here we came up with a deviation of 0.49%. And this is really reflecting also what we get in the model. The second thing, what we did, we took some of the samples. So we have 75, we have 80, we have 85, we have 95, and up to 125. We took 3 tablets, one nominal, one low dose, one high dosed. We gave this to the reference analysis for the HPLC. Based on that, we calculated the reference values. So you see here from the normal tablet, we have the reference data here. We have it for one of higher dosed and again, even higher dosage form. And we just compare this with the measurement of our CU120. And you see now, if you just compare API fraction, mass, plus content uniformity, how close we come to the data. So it was 74.08 by HPLC, and weighting cell to measure the content uniformity, we have 74.32, 96.49, 94.80, 1895, 10796. And now, let me know, is this sufficient? And please don't forget, we do this for 100%, so for each individual tablet, up to 120,000 per hour. Okay, just that you don't forget, this was the nominal mass, that you have a reference where we are with our tablets. Let's also conclude here on the case studies from Novartis. So also here we did successful spatial spectra acquisition and modeling. Root mean square of prediction was 1.63. Correlation coefficient this time printed out here. So we saw that this offers us really an opportunity to measure 100% the mass and the fraction, and from this we can achieve the content uniformity in a pharmaceutical industrial production environment. Also, we see that the CU120 machine supports real-time release, and here I would like to point out, this is our nice article from Novartis, what you can find in the Journal of Pharmaceutical and Biomedical Analysis. So if you like to read it, let me know, I can send you a copy. Here I would like to thank all the guys who were inside and contributed to the trials from AstraZeneca, from our guys, Francois and Freddy from Pharma Technology, and also Markus Krummer, Yves Rogo, and Laurent Polegatti from Novartis. Before I would like to thank you for your attention, I would like to ask you guys if you just can play my video, because this is also maybe concluding everything what I told you today, and maybe you like it. But sorry, it's again me what you will see in the video. So sorry about that.
Hello everyone, welcome to our latest innovation, the CU120 Tablet Inspection Platform. My name is Sven Borchert. I'm the Sales Product Specialist in the Quality Control Division of Pharma Technology. And now, let's talk about 100% Content Uniformity Inspection. This brand new system is a world premiere in the industry for high-speed Content Uniformity Inspection. It measures individual API fractions and mass of each single tablet up to 120,000 per hour. The machine has 3 inspection technologies on board, arranged along one single line. A 3D laser scanner gives us the tablet thickness and diameter. A NIR, infrared spatially resolved spectrometer, measures API fractions. And a 3D microwave resonator which provides the tablet mass. The unit can be used in 2 modes, offline as a batch saver and inline as an advanced PAT tool. The CU120 can therefore support real-time release testing for content uniformity and uniformity of mass. The main key benefit of the CU120 is being a versatile inspection platform, thanks to its multiple embedded technologies. The machine predicts in real time 100% content uniformity, resulting from the individual tablet API fractions and mass measurements up to 120,000 tablets per hour. Additionally to that, the diameter and thickness of each individual tablet is measured. Besides, the CU120 allows to run up to OEB3 formulation thanks to its level of sealing. As a result of its single-lane architecture, the unit requires less maintenance and calibration time. The entire equipment is user-friendly, with fast and easy product changeover and an intuitive interface. First, the vibrating pre-feeder receives tablets from the hopper and doses them into the centrifugal bowl. From there, the tablets are aligned and distributed one by one on the conveyor belt. The fixed speed vacuumed conveyor holds the tablets in perfect position and bring it to the 3D laser scanner. This 3D laser scanner verifies the exact position of the tablets and informs the NIR probe in real time to trigger the spectral acquisition with high accuracy. At the same time, the thickness and diameter are measured for each single tablet with an accuracy of 0.1 mm. Then, the product enters the NIR SRS measuring chamber, where the NIR infrared beam penetrates the surface of the tablet and collects spectral information about the API. The re-emitted light is picked up by 9 optical fibers and transmitted to the spectrometer. The obtained spectra are converted into an API's fraction with the use of a chemometric model. After the API's fraction measurement, the tablet instantly enters the 3D microwave resonator. Inside the cavity, 3 microwaves are continuously emitted in orthogonal directions. Every tablet passing through the sensor modifies these 3 microwaves depending on their mass. Directly after the mass measurement, out-of-specification tablets are removed, while correct ones are transferred into the conform product bin by the fast reject gate. In addition, a rejection confirmation sensor guarantees that non-conform products are correctly discarded. At regular intervals, samples are deviated to the high-precision weight cell to continuously maintain the calibration of the 3D microwave resonator. The 4-parameter tester can be added as an option to measure the weight, thickness, length, diameter and hardness. While using the machine, the intuitive software guides you throughout the various steps, from the recipe setup until the final reporting. At the end, all relevant batch data are summarized into an easy-to-read batch report. Thank you for your interest. Please don't hesitate to contact us if you need any further information.